Welcome to a video lesson in MSE 287, Crystal Growth. The topic is the equilibrium shape of crystals. We are studying the textbook by Ivan V. Markov entitled Crystal Growth for Beginners, Fundamentals of Nucleation, Crystal Growth, and Epitaxy. We are using the third edition published by World Scientific in 2017. What is the theorem of Gibbs-Curie-Wulff? We are going to derive this theorem by considering a crystal in a three-dimensional medium or a 3D homogeneous medium, which could be a vapor, a solution, or a melt. We derive an expression for the equilibrium shape of a single crystal proceeding from the general condition of the minimum of the Helmholtz free energy of the system at a constant temperature and constant total volume. So this mentions the minimum of the Helmholtz free energy. In equation form, it means that the first order derivative of F equals 0. And since the total volume is constant, the first derivative of volume is equal to 0. So equation 1.21 is stated this way, and this is the equilibrium condition. We assume first that the crystal is a polyhedron confined by a limited number of different crystal faces with areas capital sigma sub n, to which a series of discrete values of the specific surface energies, another sigma sub n, correspond. So as shown, we have a polyhedron. We're looking at one side of it. And what is a polyhedron? It is comprised of faces, edges, and vertices. So the crystal has faces with area sigma sub n, and corresponding to these areas are specific surface energies, the small sigma sub n. From equation 1.21, which is the equilibrium condition, we have equation 1.22. The minimum of the Helmholtz free energy is equated to the sum of three terms, and again equal to 0. The terms have the volume part and also a surface part. P sub C is the inner pressure of the crystal, and P sub upsilon is the pressure of the vapor phase. Again, the sigma sub n are the specific surface energies. V sub upsilon and V sub C are the volumes of the vapor phase and the crystal phase, respectively. The total volume is the sum of the volume of the vapor phase and the volume of the crystal phase. And since the total volume is a constant, the derivative dV equals 0. Hence, the derivative of the volume of the vapor phase is equal to the negative of the derivative of the volume of the crystal phase. And so from equation 1.22, we can rewrite that into equation 1.23. So having the volume part and the surface part. The volume of the crystal can be considered as a sum of the volumes of pyramids constructed on the crystal faces with a common apex in an arbitrary point within the crystal. So looking at the polyhedron, the crystal being a three-dimensional object, the polyhedron has the crystal faces which serve as the bases of these pyramids. The height from the base to the apex of the pyramids is h sub n, and those apex correspond to an arbitrary point within the crystal. What is the volume of a pyramid? It's 1/3 times the height times the length of the base and the width of the base. An illustration of one pyramid constructed within the crystal is shown. And we have to sum all of these volumes of pyramids. So we have the equation for the volume of the crystal equal to 1/3 times the summation over n of the height times the area. If we want the derivative of this volume of the crystal, then we must get the derivative of each parameter. As shown in the equation, it's written in terms of the derivative of the height and then the derivative of the area. Every change of the volume with accuracy to infinitesimals of second order is equal to the shift of the surfaces sigma sub n by a distance dh sub n, as shown in the figure, so that the derivative of the volume of the crystal becomes the summation over n of the product area and the dh sub n, the shift in the distance. Thus, we can rewrite the equation for the derivative of the volume of the crystal. Looking at the right side of the equation, we have 1/3 times dv sub c. So we can group together the similar terms, and we end up with the bottom equation for the derivative of the volume of the crystal. Now it is equal to 1/2 times the sum over n of h sub n times d sigma sub n. So by combining the equations shown previously, we have equation 1.24. We substitute this equation 1.24 in equation 1.23 so that we have the sum over n of the bracketed term times the derivative of the area, d sigma sub n. The expression is equal to 0. So it follows that the bracketed term must be equal to 0. As the changes d sigma sub n, those related to the area, are independent from each other, every term in the brackets is equal to 0. So we go to Wulff's rule, or the Gibbs-Curie-Wulff's theorem, or Wulff's construction. As a result, from the one we obtained in the previous slide, we have equation 1.25, showing the difference in the pressures of the crystal phase and the vapor phase, which is equal to 2 times sigma sub n divided by h sub n, the ratio of the specific surface energy and the height h. Again, the P sub c is the inner pressure of the crystal. P sub upsilon is the pressure of the vapor phase. The difference in the pressures does not depend on the crystallographic orientation. And for the equilibrium shape, one obtains the ratio of the specific surface energy to the height h is equal to a constant. That's equation 1.26. Sigma sub n divided by h sub n equals constant. This means to say that the height h sub 1 is proportional to sigma sub 1, the specific surface energy 1. The height h sub 2 is proportional to specific surface energy sigma sub 2. And the height h sub 3 is proportional to the specific surface energy sigma sub 3. That's equation 1.26 prime. What does this say? The Wulff's construction, or the Gibbs-Curie-Wulff's theorem, states that in equilibrium, the distances of the crystal faces from a point within the crystal we now call the Wolff's point are proportional to the corresponding specific surface energies of these faces. And there's figure 1.10 to illustrate this. Figure 1.10 shows the equilibrium shape of a crystal. Wolff's point is denoted by O. The distance from Wolff's point to the contact plane is denoted by H sub m. The distances H1 and H2 to the free surfaces remain the same as in a free polyhedron. And then the equilibrium shape in the absence of a foreign substrate is shown by the additional dashed line. So what's important here, one of the things important here is that the distances H1 and H2 are distances from the Wolff's point to free surfaces of a free polyhedron. According to the Gibbs-Curie-Wulff theorem, we can construct the equilibrium shape by the following procedure. We draw vectors normal to all possible crystallographic faces from an arbitrary point. Then distances proportional to the corresponding values of the specific surface energies are marked on the vectors, and planes normal to the vectors are constructed through the marks. And I have this illustration. So this is the arbitrary point in the crystal, mark O. And from there we draw the distance represented by the arrow, the vector, toward the crystallographic face. Another one is drawn from Wolff's point to another crystallographic face. And we draw the plane. So those distances are the H1 and H2. H1 is proportional to the specific surface energy, sigma 1, according to the Gibbs-Curie-Wulff theorem. In the same way, H2 is proportional to specific surface energy, sigma sub 2. Sigma sub 2 equals H2 times a constant. Then we can draw other vectors from the origin O to crystallographic faces until we draw the polyhedron. So the resulting closed polyhedron is the equilibrium shape. In addition, crystal faces with the lowest surface energies belong to it. The proportionality constant in 1.26 is determined by the difference of the pressures in the crystal phase and the vapor phase. And in the earlier sections, we saw that this difference in the pressure times the molar volume is equal to the change in the chemical potential, or the delta mu. The condition, the difference in the pressures equal to a constant, is thus equivalent to the statement that the difference of the chemical potentials, meaning the supersaturation, the difference in the chemical potential of the vapor phase and the chemical potential of the crystal phase, they have the constant and the same value all over the crystal surface. So combining the two equations for the difference in the pressures, we have equation 1.27. The supersaturation, or the difference in the chemical potential, is now equal to 2 times the specific surface energy, sigma sub n, times the molar volume divided by the distance h. What is this saying? This means that the supersaturation determines the scale or the size of the crystal. This equation 1.27 has the familiar form of the Thomson-Gibbs equation, which was discussed in earlier sections of our textbook. As Wolff's point has been arbitrarily chosen, we can take it in the center of the crystal. Now, in the same way, we can derive Gibbs-Curie-Wulff's theorem for a crystal formed on a foreign substrate. Again, we refer to figure 1.10. In this case, the crystal lies with one of its faces with a specific surface energy, sigma sub m, on the substrate. The substrate has a specific surface energy, sigma sub s. An interfacial boundary is formed between the crystal and the substrate. Then we want to find this specific energy. So we will perform an imaginary experiment. But before we do that, let's look again at figure 1.10, illustrating the equilibrium shape of a crystal on a foreign substrate. So Wolff's point is denoted by O. The distance from Wolff's point to the contact plane is denoted by H sub m. And in this case, where there is a foreign substrate, the distances H1 and H2 to the free surfaces remain the same as in a free polyhedron. So we see that the crystal having the specific surface energy sigma sub m lies on the substrate. And it's pointed by the arrow. The interfacial boundary is formed, and this is identified by the arrow. Okay? Now, the relation of Dupré. This is the imaginary experiment. So we consider two crystals, A and B, representing the substrate and then the deposit, respectively. They have equal dimensions. We cleave them in a reversible and isothermal fashion, thereby producing two surfaces of crystal A and two surfaces of crystal B. Each surface of crystal A has an area denoted by sigma A, and each surface of crystal B has area denoted by sigma B. Sigma B, or area of crystal B, is equal to the area of crystal A. In doing this cleaving, we expend energies UAA related to crystal A and UBB related to crystal B. Then we put the two halves of A in contact with the two halves of B, thereby producing two interfacial boundaries AB. And each of these interfacial boundaries has an area denoted by sigma sub AB, which is also equal to the areas of crystal A and the area of crystal B. Figure 1.9 illustrates the process, illustrates the imaginary experiment. So we have crystals A and B, and we cleave them. And the two halves are joined, forming AB and AB. So you have two interfacial boundaries, AB and AB. The work gained is negative 2U sub AB. The excess energy of the boundary AB required to balance the energy change accompanying the process is 2ui. 2ui equals energy spent plus the energy gain. In the case that the two crystals are indistinguishable from each other, then the energies UAA is equal to energy UBB and energy UAB. And so the excess energy UI is equal to 0. Then we use the definition of the specific surface energy. Sigma sub HKL equals the work done divided by 2 times the area. There's always the factor 2 because in the process of separating the crystals, you form 2 surfaces. And then we obtain the well-known relation of Dupre, equation 1.28. Sigma sub I equals sigma sub A plus sigma sub B minus beta. So I'm going to show the steps. So from the equation showing the energy spent plus the energy gained, the equation showing that, we divide that equation by the factor 2 times sigma sub AB. And this is the result. So on the right side, we have the term U sub AA divided by 2 times sigma AB, which can be written as energy UAA divided by 2 times the area of crystal A. Because as defined earlier, the area of the interfacial boundary is equal to the area of crystal A. Then we let this ratio be sigma sub A. And then the next term in the equation on the right, U sub BB, the energy associated to crystal B divided by 2 sigma sub AB is equal to energy UBB divided by 2 area of crystal B. And we let this ratio be sigma sub B. And simplifying, we have equation 1.28. So the term on the left side, sigma sub I is equal to U sub I divided by the area of the interfacial boundary. This is the specific surface energy. It is defined as the excess energy of the boundary per unit area. And the parameter beta on the right side of the equation is equal to energy U sub AB divided by the area of the interfacial boundary. This is the specific adhesion energy. It is defined as the energy per unit area to disjoin 2 different crystals. This accounts for the binding between the 2 crystals. This parameter beta does not depend on the lattice misfit. What is the lattice misfit? It's the difference in the lattice parameter of substrate and then the layer divided by the lattice parameter of the substrate. The lattice misfit will be taken into account when considering the epitaxial growth of thin films. When a crystal is formed on a foreign substrate, there is energy lost and energy gained. A surface energy is lost, that's sigma sub S times sigma sub M. The surface energy gained is sigma sub I times sigma sub M. sigma sub m is the area of the contact. Instead of equation 1.22, we have equation 1.29 for the minimum of the Helmholtz energy. So again, we have terms showing the volume part and terms showing the surface part. So the fourth term is the addition. Something new, differentiating this from equation 1.22. And from here, we derive the Wulff-Kaishu theorem. Equation 1.30 shows that sigma sub n divided by h sub n is equal to sigma sub m minus beta all over h sub n, equal to a constant. This means to say that the distance h1 is proportional to sigma 1, or the specific surface energy 1. And the distance h2 is proportional to the specific surface energy sigma 2. And the distance h3 is proportional to the specific surface energy sigma 3. And the distance h sub m is proportional to the specific surface energy sigma m minus beta. So we remark that in the presence of a substrate, an interface is formed instead of a surface. And that's illustrated in figure 1.10. So the distance h sub m from the Wulff's point to the contact plane is proportional to the difference of the corresponding specific surface energy and the specific adhesion energy. Sigma sub m minus beta is equal to h sub m times a constant. When the substrate catalytic potency is equal to 0, the adhesion energy beta is equal to 0. The distance h sub m will have its homogeneous value in the absence of a substrate. In this case, we speak of complete non-wetting. At the other extreme, when the value of beta is 2 sigma, resulting from the sum of sigma A and sigma B, where sigma A is equal to sigma B equal to sigma. Then we have the case of complete wetting, and the crystal will be reduced to a two-dimensional monolayer island. In all intermediate cases, for values of beta in between the extremes, for beta greater than 0 and less than 2 sigma, we have incomplete wetting, and then the height of the crystal will be smaller than its lateral size. So we have the following example, figure 1.11, showing the effect of the wetting on the equilibrium shape of a crystal on a foreign substrate. So we'll look at illustrations A to E. In the case of a free polyhedron, the distance from Wulff's point to the crystal face, denoted by H1, and the distance from Wulff's point to another crystal face, denoted by H2. The values are proportional to sigma 1 and sigma 2 respectively. That is according to the Gibbs-Curie-Wulff theorem. And then if we draw the vector from Wolff's point to another crystallographic phase, as shown in the illustration, that distance is also proportional to the specific surface energy of that crystal phase. Now, in the presence of an unlike substrate, what will happen to distances h1 and h2? Answer is they will remain to be proportional to the specific surface energy. Okay, so understand that the equilibrium shape has free surfaces and has a surface that is in contact with a substrate. For those surfaces called the free surfaces, the distance from the Wolff's point will always be proportional to the specific surface energy. But for the distance to the contact plane, that will be proportional to sigma I minus beta, according to the Wolff-Cauchy theorem. So note that we simply had a change of variable from h sub m to h sub I. So again, h sub I is proportional to sigma sub I minus beta. That's the distance from the Wolff's point to the contact plane. In the next illustration, what happens when beta equals 0? The specific adhesion energy is equal to 0. Then the distance from the Wolff's point to the contact plane will be proportional to sigma sub I. Recall that sigma sub I minus beta all over h sub I is equal to a constant. If we take the constant to be equal to 1, and then beta is equal to 0, then h sub I equals sigma sub I. This is the case for complete non-wetting. In the next case, we have distances from Wolff's point, h1, h2, and hi. h1 is proportional to sigma 1, h2 is proportional to sigma 2. Those are free surfaces with a specific surface energy. Then what's important is the h sub I, the distance from Wolff's point to the contact plane. This is what happens when the beta is equal to 0.25 sigma I. Plugging this value in the equation, we have h sub I equals sigma I minus 0.25 sigma I. And the result is the distance h sub I is equal to 0.75 sigma sub I. So this is a lesser value than the previous one. So as shown in the illustration, the length of the vector h sub I is also lesser than the previous example. This is the case of incomplete wetting. In this next illustration, we notice that the distance h sub I is pointing to the negative direction. It has a negative value. This happens when the beta is equal to 1.75 sigma sub I, as an example. Plugging that in the equation, h sub I is equal to sigma sub I minus 1.75 sigma sub I, resulting to negative 0.75 sigma sub I. Okay, so we notice a negative value for h sub I. This is a case of incomplete wetting. Then finally, we notice that the distance h sub I from Wolff's point is still pointing to the negative direction, and it has a larger value than the previous one. So this is the case that happens when beta is equal to 2 sigma I. When you plug it in the equation, you obtain negative sigma sub I for h I. So those are the examples we covered. So let me ask you, can you now draw the equilibrium shape of a crystal in contact with a substrate for certain values of beta? So this task is left to the student. A problem set will be assigned. So that's the end of this video lesson. Thank you.